The numerous irregularities in the cosmic microwave background, CMB, and other astronomical observations suggest that there may be something essential missing in our understanding of the universe. One proposed solution comes from circle quantum cosmology, a framework that originates from circle quantum gravity. In this model, the universe does not begin from a singular, infinitely dense point as the Big Bang theory suggests. Instead, it posits that the universe may have undergone a contraction and subsequent expansion, akin to a phoenix rising from its ashes. Circle quantum cosmology introduces the concept of a minimal scale, around 1.0 times 10 to the power of negative 35 meters, below which spacetime cannot be described in conventional terms. This suggests that the universe could not have originated from an infinitesimally small, infinitely dense point as described by the traditional Big Bang theory. Instead, the universe might have emerged from a previous, contracting cosmos, expanding again in a cyclical manner. This idea is not entirely new, but circle quantum cosmology provides a mathematical framework that supports cyclic time and a potential big bounce, similar to the concept of a big crunch followed by another expansion. If this theory is correct, the early universe would have been characterized by a delicate energy and density that could explain some of the observed irregularities in the CMB, such as subtle temperature variations across the sky. These variations, measured through the energy spectrum, provide significant evidence of the universe's origins, further supporting the idea of a bounce rather than a singular Big Bang. Circle quantum cosmology offers a compelling explanation for some long-standing anomalies in cosmology, and may provide new insights into the very origins of the universe. It also presents a possible explanation for the observed discrepancies in the temperature of the CMB across different regions of the sky. The framework proposed by circle quantum cosmology accounts for these discrepancies, aligning with the expected behavior of large-scale structures and gravitational lensing effects. However, while the idea of the universe originating from a tremendous bounce has been proposed before, its full implications require further exploration. One major challenge to cyclic cosmology is the concept of entropy, or the increasing disorder within a system. In cyclic models, entropy would accumulate over each cycle, leading to increasingly disordered universes. This suggests a starting point for a cosmic detonation, conflicting with the idea of an eternally existent universe. Despite these challenges, physicists like William Kenny from the University of Buffalo continue to explore the key issues within this theory. In contrast, the widely accepted inflationary Big Bang theory describes a universe that expanded rapidly from a hot, dense state and continues to grow at a slower pace. This model explains much of the observable universe, but the possibility of cyclic cosmology and the Big Bounce continues to offer intriguing solutions to the unresolved mysteries of the universe's origins. The hypothesis of how the universe began has long been a subject of intense debate among physicists. For some, the traditional view of the Big Bang as the beginning of everything is no longer the full picture. In this revised view, the universe may have existed before the Big Bang, expanding infinitely into both the past and the future. In fact, before the Big Bang, the universe was in a contracting state, which eventually led to a bounce or a second expansion event. This theory proposes that the universe could experience cycles of contraction and expansion indefinitely, with each cycle following a big bounce. However, not all physicists agree with this idea. Some, like renowned physicist Brian Cox, challenge the notion that something can emerge from nothing, adding further complexity to the debate. Moreover, recent discoveries by the James Webb Space Telescope have raised questions that directly contradict the traditional view of the Big Bang as the universe's origin, suggesting that the Big Bang may not have been the true beginning of the cosmos. If the Big Bang wasn't the universe's origin, what then was the true start of the universe? This question touches on ideas that have existed since the early 20th century, when Georges Lemaitre proposed the concept of an expanding universe in 1927. While most modern cosmologists still believe in the Big Bang as the origin of the universe, there are some who maintain that this is merely the beginning of our observable universe and not the ultimate beginning of all existence. The universe, as we understand it, is defined by an inflationary period that occurred before the Big Bang. During this inflationary period, the universe was nearly empty, devoid of matter and radiation. Space itself was filled with an immense amount of energy. Over time, this energy transformed into matter and radiation, leading to rapid changes in the universe's structure. These changes were governed by the laws of physics and, as the universe continued to expand, new particles and structures began to form, laying the groundwork for the universe as we know it today. The concept of inflationary expansion helps to explain some of the early stages of the universe's evolution. During this period, space expanded at an accelerated rate, leading to the formation of the cosmic structures we observe today. As the universe continued to expand, it cooled down, and matter began to condense into galaxies, stars, and other celestial bodies. Yet, despite our understanding of the universe's current expansion, many questions remain unanswered about the true origins of the cosmos. In this framework, the universe's expansion did not begin with a simple bang, but rather with a rapid inflationary phase that set the stage for the more gradual expansion we observe today. While the initial conditions of this inflationary period were governed by quantum fluctuations, they eventually gave rise to the large-scale structures we see in the universe. These fluctuations are visible in the cosmic microwave background, CMB, which provides us with a snapshot of the early universe, revealing temperature and density variations that hint at the universe's initial conditions. However, there are still many inconsistencies in our understanding of the early universe, especially regarding the cosmic microwave background. These inconsistencies suggest that the full story of the universe's origin may be far more complex than we previously thought. Cyclic quantum cosmology, CQC, and its implications continue to inspire exploration of fundamental cosmological issues, particularly regarding the universe's origins. One key question that persists is whether the universe ever had a definitive beginning. Some advocates of cyclic models argue that it did, but this raises significant challenges about the nature of the event that initiated everything. In contrast, traditional cosmology suggests an eternal universe that has always existed, evolving through cycles of expansion and contraction. However, physicist William Kenny from the University at Buffalo points out a crucial flaw in the idea of an eternally cyclical universe: entropy. In cyclic cosmology, each cycle increases the degree of disorder in the system, leading to the inevitable conclusion that the universe's beginning would have been preceded by a Big Bang or similar event. This contradicts the notion of an infinite, unchanging cosmos. The universe indeed expanded, with this process continuing at a slower rate, eventually leading to the cosmos we observe today. This scenario is consistent with the inflationary model of the Big Bang, which is the most widely accepted explanation for the observable universe's current state. Observations from the cosmic microwave background, CMB, and the irregularities in the distribution of galaxies further support this model, suggesting that something crucial remains unexplained in our understanding of the universe. One intriguing proposal arises from CQC, which stems from quantum gravity theory. CQC posits that there is a minimum size, or Planck scale, at which quantum effects dominate. This implies that the universe could not have existed in a state of infinite density at the time of the Big Bang. Instead, it would have experienced quantum corrections and pressure that prevented a truly singular, infinitesimal state. In this framework, the universe could have undergone a bounce from a previous contracting state, similar to a phoenix rising from the ashes. While this idea is not entirely new, CQC provides a mathematical structure to support its cyclic model. According to CQC, the early universe may have been much smoother and more uniform, with lower energy and density. This concept could explain the subtle variations in temperature seen across the sky in the CMB, which serve as significant evidence for the universe's early conditions. Additionally, the theory could account for some of the long-standing anomalies in cosmology, such as the temperature discrepancies between the two hemispheres of the CMB sky. The mathematical framework of CQC also helps address some of the challenges associated with understanding the universe's origin. It may offer insights into the strange behaviors observed at vast cosmic distances and help explain the mysterious lensing effects observed in the cosmic sky. Dr. Vetko from the National Institute of Advanced Studies suggests that these phenomena may not be simple observational errors but could result from quantum gravitational effects that occurred during the early universe. The idea of a big bounce as the origin of the universe has been proposed before, but its acceptance requires further investigation and exploration. The immense scale of the universe presents a challenge for supporting such theories, and our ability to observe and understand the universe is constrained by our current limitations. Expert Dwayne Johnson, a renowned cosmologist, emphasizes that while these ideas hold promise, they also require more evidence and refined methodologies to gain broader acceptance. In conclusion, while CQC and other cosmological theories continue to challenge conventional thinking, they also offer new avenues for addressing fundamental questions about the universe's origin and its cyclical nature. These advancements may eventually lead to a more comprehensive understanding of the cosmos and its true beginnings.